Okay, class. Today we're going to learn about conservation of mechanical energy. So recall from today we discussed different forms of energy, and there are lots of different forms. That's one of the reasons why scientists and students have a hard time conceptualizing about energy. There are just so many different forms. We're going to focus on only two of those forms, one of them being potential energy due to gravity. And the way we'll be able to calculate that is by multiplying the mass times the acceleration due to gravity times the height. There are also other forms of potential energy which we discussed in class today. Elastic potential energy from springs and bows and arrows, and also electric potential energy. We're not going to be discussing those currently. Also, another form of energy we're going to be investigating is kinetic energy. And kinetic energy is another form of mechanical energy. And you can calculate the amount of kinetic energy an object has by multiplying 1/2 times the mass times the square of the velocity of the object. There are other forms of energy like thermal, nuclear, and chemical energies as well. But for just this portion of the class, we're going to focus on kinetic and gravitational potential energy. So the unit of energy, what we're going to measure energy with, is called the joule. And a joule comes from, let's look at the formula for potential energy, a unit of mass times a unit of acceleration due to gravity times a unit of height. And so a unit of mass is a kilogram, a unit of acceleration due to gravity is a meter per second each second, and the unit of height is the meter. And if you multiply the meters in the numerators, you get kilogram times a meter squared per second squared. And we've renamed this base unit of energy after James Prescott Joule. So the unit of energy we'll be using will be the joule. Notice kinetic energy has the same unit, a unit of mass times a unit of velocity squared. Well, a unit of mass is a kilogram, and a velocity unit is meters per second, but we have to square both the numerator and the denominator. We also get a joule. Well, conservation of mechanical energy says that, and we learned this today in our lab with the skater and the half pipe, that the total mechanical energy of an object will remain, what do you think goes here, if there is no work done on the object. And we'll learn about work later. Yeah, this word is constant. And remember, the word constant means the same thing as conserved. If we're conserving something, we're sort of keeping it the same. So we talked about today's in class. We like to conserve our natural resources. So when we chop, 1,000 trees down to make paper, we're probably going to plant 1,000 trees as well, and therefore we're conserving our natural resources. Well, with energy, it's naturally conserved. We don't have to do anything. It is automatically done for us. If we lose one form of energy, you can be sure that another form of energy is increasing. Another way of saying this is that energy can change forms, but the total amount always remains constant. So let's look at an example that we looked at today in class. A ball rolling down a hill. In fact, yesterday in class, you actually made some calculations and some measurements. So if we look at a ball at the top of a hill of height h, we'll notice that all of the energy of that ball, before we've released it, is in the form of potential energy. As the ball rolls down the hill, it will gain kinetic energy, but because it's losing height, it will lose potential energy. So much, in fact, that as you get halfway down the hill, the potential energy will be half of its original value, and kinetic energy will make up the other half of the total amount of energy, which is remaining constant. Now, if we go all the way and let the ball roll all the way down the hill to the bottom of the hill, the ball will continue to gain kinetic energy, continue to lose potential energy because the height is decreasing, until all of our energy becomes what type of energy? You've got it. It's going to become all kinetic energy. So what do you notice about the potential energy at the top of the incline here compared to the kinetic energy at the bottom of the incline here? Well, even though we haven't calculated anything, you can see that the potential energy at the top before we released it equals the kinetic energy at the bottom. And another way of stating this is that total energy remains constant. And there are two parts of total energy that remain constant that we're talking about in this unit: potential and kinetic. So our initial potential plus kinetic energy equals our final potential plus kinetic energy. It actually equals our potential plus kinetic energy anywhere along the path of that ball. Well, we know that potential energy is mass times acceleration due to gravity times height. Remember from last term that mass times acceleration due to gravity, this is what we call the weight of the object in newtons. So you could just multiply that by the height and also get the potential energy. And then the kinetic energy is 1/2 m times v squared. So the sum of the potential and kinetic energies at the beginning equals the sum of the potential and kinetic energies in the end. So let's solve a problem involving conservation of energy. Let's take a child on a swing set who's lifted to 1 meter off the ground. How would we be able to calculate the speed of the child at the ball